Chapter 8, Internal Flow. This chapter discusses fluid flow inside pipes, which is essential in engineering applications such as water supply, oil transport, and industrial processes. The main focus is how fluids behave when flowing in closed conduits. The concepts include differences between laminar and turbulent flow and their impact on energy losses. The discussion links theoretical principles with practical piping applications. Understanding this chapter is fundamental for analyzing piping networks and pumping systems.
Lesson Plan Fluid Mechanics 1. This slide shows that internal flow is a logical continuation of previous chapters, such as fluid statics, Bernoulli, and momentum analysis. Each earlier chapter builds the foundation for understanding flow behavior in pipes. Internal flow requires simultaneously understanding of energy, momentum, and fluid properties. With this structure, students can see the connection between different topics in fluid mechanics. This chapter serves as a bridge between basic theory and real system applications.
Learning outcome. The learning outcomes emphasize a deep understanding of laminar and turbulent flow and the concept of fully developed flow. Students are also expected to calculate major and minor losses in piping systems. Pumping power requirements become an important part of system analysis. This topic also introduces various methods for measuring velocity and flow rate. All these outcomes are essential for designing and evaluating real fluid systems. Internal flows in industry. This image shows that piping systems are widely used in almost all industries. Internal flows are found in refineries, chemical plants, and utility systems. Pipes, elbows, T's, and valves are the main components used to direct fluid flow. Each component affects pressure losses and system performance. Therefore, internal flow analysis has very high practical value.
Circular versus non-circular pipes. Circular pipes can withstand large pressure differences without shape distortion. Stress distribution in a circular cross-section is also more uniform than in other shapes. This makes circular pipes the main choice for high-pressure systems. In contrast, non-circular ducts are usually used in low-pressure systems, such as air ducts. The choice of cross-sectional shape strongly affects system strength and reliability. Laminar pipe flow velocity formula. The average velocity is defined as the mean fluid speed across the pipe cross-section. In fully developed laminar flow, the velocity profile is parabolic, with a maximum value at the center of the pipe. The velocity decreases toward the wall due to friction effects. An important relationship is that the average velocity equals half of the maximum velocity. This concept is essential for flow rate and energy calculations.
Check your understanding number 1. In fully developed laminar flow, the average velocity is half of the maximum velocity.
Flow regimes in candle smoke. The candle smoke example is used to visualize the difference between laminar and turbulent flow. Near the source, the flow appears smooth and orderly, indicating laminar flow. Farther away, the flow becomes irregular and chaotic, indicating turbulent flow. Between these two regions, there is a transitional and unstable flow zone. This phenomenon helps in understanding the basic nature of flow regimes.
Dye injection experiment clearly shows the difference between laminar and turbulent flow. In laminar flow, the dye remains as a straight line and does not mix. In turbulent flow, the dye quickly disperses and mixes with the surrounding fluid. This indicates intense mixing in turbulent flow. This behavior is important in mixing and chemical reaction applications.
Reynolds number insights. The Reynolds number represents the ratio between inertial and viscous forces.
This value is the main indicator to determine whether the flow is laminar or turbulent. The Reynolds number depends on flow velocity, characteristic length, and kinematic viscosity. Small values indicate viscous-dominated flow, while large values indicate inertia-dominated flow. Therefore, the Reynolds number is a key parameter in internal flow analysis.
Hydraulic diameter overview. The hydraulic diameter is used to represent the characteristic size of flow in non-circular ducts. This concept relates the flow cross-sectional area to the wetted perimeter. For circular pipes, the hydraulic diameter is equal to the actual diameter. This approach allows pipe flow equations to be applied to many different channel shapes. Therefore, flow analysis in ducts and channels becomes more uniform and consistent.
Check your understanding number 2. What does the hydraulic diameter represent in fluid flow analysis? C. The ratio of flow cross-section area to the wetted perimeter. Explanation. A is incorrect because the hydraulic diameter is not always the actual diameter of circular pipes. It generalizes to non-circular ducts as well. B is incorrect because the hydraulic diameter does not directly relate to velocity and pressure drop, but is used in determining flow characteristics. D is incorrect because the hydraulic diameter is not related to the length of the pipe segment, but to its cross-section and wetted perimeter. Transitional flow characteristics. Transitional flow occurs between the laminar and turbulent regimes within a certain Reynolds number range. In this condition, the flow behavior becomes unstable and difficult to predict. The die trace may alternate randomly between smooth and chaotic patterns. Instability increases because inertial forces begin to overcome viscous effects. This region is important because it marks the onset of turbulence.
Hydrodynamic entrance region. At the pipe entrance, the velocity profile is still developing because wall effects have not yet reached the entire cross-section. The velocity boundary layer starts growing from the wall toward the center. Near the inlet, there is still a core region with nearly uniform velocity. As the distance increases, the boundary layers meet at the center, and the profile becomes stable. The distance required to reach this condition is called the hydrodynamic entrance length. Velocity boundary layer in pipes. The nearly irrotational core flow exists only in the initial region, before the boundary layer fully develops. The boundary layer forms along the wall and reduces the velocity near the surface. In the entrance region, the velocity profile continues to change until it becomes stable. For laminar flow, the fully developed profile is parabolic. For turbulent flow, the profile is flatter or fuller near the center. Fully developed pipe flow. In fully developed flow, the velocity profile no longer changes along the flow direction. This indicates that the flow has reached a hydrodynamically steady condition. The wall shear stress becomes constant along the pipe. For laminar flow, the parabolic profile shape remains the same from one cross-section to another. This condition greatly simplifies the analysis of pressure loss and friction forces. Entrance length and wall shear stress. The wall shear stress is high near the pipe entrance because the velocity profile is still developing. Along the entrance region, its value decreases until it reaches a constant level. This change is directly related to the evolution of the velocity profile shape. After passing the entrance length, the flow enters the fully developed region. In this region, both the wall shear stress and velocity profile no longer change with position. Wall shear stress in pipes. In the entrance region, the wall shear stress changes significantly because the flow is still adjusting. Its value is high near the inlet and then gradually decreases. Once the flow is fully developed, the wall shear stress becomes constant along the pipe. This change reflects the formation of a stable velocity profile. This shear stress strongly influences energy losses in piping systems.
Check your understanding number 3. The hydrodynamic length marks the transition from the entrance region to fully developed flow in a pipe.
Differential fluid element analysis. A ring-shaped fluid element is used to analyze laminar flow inside a pipe. For this element, a force balance between pressure forces and shear forces is performed. From this force balance, the velocity distribution equation can be derived. The result shows that the velocity profile is parabolic for fully developed laminar flow. This approach provides a strong theoretical foundation for pipe flow equations.
Force balance in laminar flow. A disc-shaped fluid element is used to derive the relationship between pressure drop and wall shear stress. A force balance is performed between pressure forces on both sides of the element and the shear force at the surface. From this analysis, the relationship between the pressure gradient and shear stress distribution is obtained. This equation becomes the basis for deriving the laminar velocity profile. This approach shows how basic mechanics laws are applied in pipe flow analysis. Pressure and head loss. Pressure loss represents the energy lost due to friction during flow in a pipe. This quantity is often expressed as head loss, which represents energy loss per unit weight of fluid. The relationship between pressure loss and head loss allows the use of energy equations in hydraulic systems. This concept applies to both laminar and turbulent flows. This understanding is essential for the design and evaluation of piping systems. Check your understanding number 4. What does head loss in pipe flow primarily represent? C. The pressure drop converted to elevation loss in hydraulic systems. Explanation. A is incorrect because head loss does not directly represent the energy required to pump fluid, though it influences it. B is incorrect because head loss is not related to the relationship between velocity and flow rate, but to energy losses due to friction. D is incorrect because head loss does not measure turbulence intensity, but rather the loss of energy in the flow system.
Pumping power and pipe diameter. Pipe diameter has a very strong influence on the required pumping power. When the pipe diameter is increased, the flow velocity decreases, and energy losses are greatly reduced. Theoretically, doubling the pipe diameter can reduce pumping power by a factor of 16 for laminar flow. This shows the importance of diameter optimization in system design. Proper diameter selection can significantly improve energy efficiency.
Laminar flow in inclined pipe. In an inclined pipe, in addition to pressure and shear forces, the weight component of the fluid also affects the flow. The pipe inclination can either assist or oppose the flow direction. If the flow moves upward, gravity resists the motion and reduces the velocity. If the flow moves downward, gravity helps accelerate the flow. This analysis is important for piping systems with elevation differences.
Laminar flow relations. For horizontal pipes, the flow is driven purely by the pressure difference, without gravitational effects. In inclined pipes, gravity must be included in the flow equations. The sign of the inclination angle determines whether gravity accelerates or decelerates the flow. These relations allow the calculation of velocity and flow rate for different pipe orientations. Thus, laminar flow equations become more general and flexible. Friction factor for laminar flow. The friction factor depends only on the Reynolds number. This relationship is simple and can be written as F equals 64 divided by RE. For non-circular cross-sections, the friction factor is also influenced by the geometry of the shape. However, the variation is relatively small for many practical shapes. This concept shows that laminar flow has predictable friction characteristics.
Check your understanding. Number 5. For circular pipes, the friction factor depends only on the Reynolds number.
Reynolds number. This photo shows the change in flow pattern of water coming out of a pipe. At low velocity, the flow appears smooth and orderly, indicating laminar conditions. As the velocity increases, the flow starts to oscillate and eventually becomes turbulent. This change is directly controlled by the Reynolds number. This visual example helps in understanding the physical meaning of flow transition. Flow characteristics from a tube. The previous example shows how flow characteristics change as the velocity increases. At low velocity, the flow remains laminar and stable. At higher velocity, the flow becomes turbulent with complex eddy structures. The Reynolds number is used as the main criterion to determine this change. This observation is often used in basic fluid mechanics experiments. Turbulent flow mixing. Turbulent flow enhances momentum transfer because fluid particles with different velocities continuously mix. This mixing process makes the distribution of velocity and fluid properties more uniform. Interactions among particles also increase energy exchange within the flow. As a result, turbulent flow is very effective for mixing processes. However, this condition also causes larger energy losses. Velocity fluctuations in turbulent flow. In turbulent flow, the velocity consists of a mean component and random fluctuations with time. These fluctuations reflect the irregular and highly dynamic nature of the flow. The velocity variations contribute to energy dissipation in the system. Physically, mechanical energy is converted into thermal energy through this process. Therefore, turbulent flow is always associated with larger energy losses. Velocity and shear stress in turbulent flow. The velocity profile in turbulent flow is flatter near the pipe center and changes very steeply near the wall. The total shear stress consists of contributions from both laminar and turbulent effects. Near the pipe center, the turbulent component is dominant. Near the wall, viscous effects become more important and increase the velocity gradient. This distribution explains why turbulent flow has high friction. Check your understanding. Number 6. What dominates the shear stress near the center of a pipe in turbulent flow? B. Turbulent shear stress. Explanation. A is incorrect because laminar shear stress is more significant near the walls rather than the pipe center. C. Incorrect because wall friction effects primarily influence the boundary layer rather than the pipe center. D. Incorrect because radial velocity changes are related to the velocity profile, not directly to the shear stress dominance. Velocity fluctuations and momentum transfer. Vertical velocity fluctuations cause fluid particles to move across different flow layers. This movement carries momentum from one layer to another. As a result, momentum exchange becomes much more intense than in laminar flow. This mechanism is a key characteristic of turbulent flow. This effect explains why turbulent flow is more efficient for mixing. Velocity gradients and shear stress. In laminar flow, the velocity gradient near the wall is relatively small, resulting in low shear stress. In contrast, in turbulent flow, the velocity gradient near the wall is very large. This causes the wall shear stress to become much higher. Although the turbulent boundary layer is thicker, the velocity change near the wall is very steep. This is one of the main reasons for the large energy losses in turbulent flow. Velocity profiles in pipe flow. In laminar flow, the velocity profile is parabolic, with maximum velocity at the center and zero at the wall. In turbulent flow, the profile is fuller and less peaked at the center. The turbulent flow structure also consists of several layers, such as the viscous sublayer and the turbulent core. These differences in profile shape strongly affect energy and friction calculations. Therefore, choosing the correct flow model is very important in engineering analysis.
Velocity profiles in turbulent flow. Near the wall, there are several flow regions, such as the viscous sublayer, buffer layer, and overlap layer. In the layers, the velocity profile follows a logarithmic law. This law has been widely validated by experiments. The velocity scaling in each region is different and affects the shear stress distribution. This layered structure is a characteristic feature of wall-bounded turbulent flow.
Check your understanding number 7. The overlap layer in wall-bounded flows follows a logarithmic velocity profile, supported by experimental data. Turbulent versus laminar velocity profiles. The laminar velocity profile shows a large variation from the center to the wall. In turbulent flow, the profile becomes flatter as the power law exponent increases. A flatter profile indicates a more uniform velocity distribution. This means that most of the fluid moves at nearly the same speed. This difference is very important in flow rate and energy loss analysis. Colebrook equation overview. The Colebrook equation is used to determine the friction factor for turbulent flow in pipes. This equation is implicit and cannot be solved directly without iteration. The friction factor depends on the Reynolds number and the relative roughness of the pipe. Therefore, calculations usually use numerical methods or the Moody chart. This equation is very important in engineering piping system design.
Pipe roughness values. Each pipe material has a different level of surface roughness. Materials such as glass and plastic are considered very smooth and produce small friction losses. Materials like steel or copper have moderate roughness. Concrete and cast iron have much higher roughness and therefore increase energy losses. These roughness values must be considered in turbulent flow calculations.
Friction factor and roughness. On this slide, we examine how pipe surface roughness influences the friction factor and, consequently, fluid flow resistance. First, consider smooth pipes. When the inner wall surface is smooth, the fluid encounters less obstruction as it moves through the pipe. As a result, the friction factor becomes relatively low, meaning there is less energy loss due to friction. In engineering systems, smooth pipes are often preferred because they reduce pumping power requirements and improve flow efficiency. Now, let us look at increasing roughness. As the pipe surface becomes rougher, tiny protrusions or irregularities on the wall disturb the flow near the boundary. These surface imperfections increase resistance to motion, causing the friction factor to rise. In practical terms, rougher pipes require more energy to maintain the same flow rate because additional pressure losses occur. Another important point is flow dependency. In this discussion, we assume the Reynolds number remains fixed. By keeping Reynolds number constant, we isolate the effect of roughness and clearly.
Moody chart insights. The Moody chart combines the effects of Reynolds number and relative roughness on the friction factor. In the laminar region, the friction factor decreases sharply as Reynolds number increases. In the turbulent region, the friction factor depends on both Reynolds number and roughness. In the fully rough condition, the friction factor becomes almost constant and independent of Reynolds number. This chart is a standard tool in pipe flow analysis.
Check your understanding number 8. In a fully rough, turbulent flow, the friction factor is primarily dependent on C. Surface roughness only, independent of Reynolds number. Explanation. A is incorrect because in fully rough, turbulent flow, the friction factor no longer depends on Reynolds number, but only on surface roughness. B is incorrect, because Reynolds number does not influence the friction factor in fully rough flow. D is incorrect, because pipe diameter and flow velocity contribute to Reynolds number, but do not directly determine the friction factor in the fully rough regime.
Types of pipe flow problems. In pipe flow analysis, there are usually three main types of problems. The first type is to determine the pressure loss when the geometry and flow rate are known. The second type is to determine the flow rate when the geometry and pressure loss are known. The third type is to determine the pipe diameter when the flow rate and pressure loss are specified. These three types of problems cover almost all practical design cases. Schedule 40 pipe sizes. The nominal pipe size is not the same as the actual inside diameter. Standards such as Schedule 40 are used to define industrial pipe dimensions. For small pipes, the difference between nominal size and actual diameter is quite significant. For larger pipes, the actual diameter is also defined by the same standard. Using the wrong diameter can lead to large errors in flow calculations. Minor losses in pipes. In addition to friction losses along the pipe, there are also additional losses caused by components, such as valves and elbows. These losses are called minor losses, although in many systems their magnitude can be quite large. The magnitude of these losses is expressed using a loss coefficient multiplied by the dynamic pressure. Comparing conditions with and without the component shows its effect on the flow. This concept is very important in complex piping systems. Equivalent length for components. The energy loss caused by a component can be replaced by an equivalent pipe length. This means the component is treated as an additional length of straight pipe. This approach simplifies calculations for systems that contain many fittings. In this way, all losses can be summed as if the system were one long straight pipe. This method is very practical in piping network design. Check your understanding, number 9. In flow analysis, devices like angle valves are replaced by an equivalent pipe length to simplify pressure drop calculations. Inlet head loss. At a sharp-edged inlet, the flow contracts and a vena contracta is formed. This phenomenon causes flow separation and increased energy loss. At a well-rounded inlet, the flow enters more smoothly and the energy loss is much smaller. The loss coefficient is used to quantify this effect. Good inlet design is very important for improving system efficiency. Loss coefficients for pipe components. Sudden changes in diameter, such as expansions or contractions, cause significant energy losses. Sharp inlets have higher loss coefficients compared to well-rounded inlets. Gradual changes produce smaller losses. The magnitude of the loss coefficient depends on the diameter ratio and the transition angle. This concept is important in designing efficient pipe transitions. Loss coefficients for fittings. Smooth bends produce smaller energy losses compared to sharp bends or tees. Fully open valves, such as ball valves, have small losses. In contrast, partially closed gate valves can cause very large losses. Threaded connections usually have higher losses than flanged connections. All these factors must be considered in piping system analysis. Flow contraction and head loss. When fluid enters through a sharp edge, the flow contracts and forms a vena contracta. The static pressure decreases because part of the energy is converted into kinetic energy. Flow separation occurs at the edge, causing energy dissipation. The head loss can be represented as the difference between the energy before and after contraction. The larger the loss coefficient, the greater the energy wasted. Check your understanding, number 10. What is the primary cause of energy dissipation in flow through a sharp-edged pipe? B.
formation of a vena contracta and flow separation at the sharp edge. Explanation. A. Incorrect because the conversion of velocity head to pressure head describes energy conservation, not dissipation. C. Incorrect because flow velocity is not uniform due to separation and the vena contracta. D. Incorrect because a reduction in the loss coefficient would decrease, not increase, energy dissipation.
Inlet rounding and loss coefficient. Rounding the inlet edge can significantly reduce the loss coefficient. For very sharp inlets, strong flow separation occurs, and energy loss is large. As the rounding radius becomes larger relative to the pipe diameter, the flow becomes smoother. This improves the efficiency of fluid entry into the pipe. Therefore, small geometric details can have a large impact on system performance. Flow behavior at submerged outlet. When fluid discharges into another fluid, its kinetic energy is gradually converted into thermal energy due to friction and mixing. In the outlet region, a highly turbulent mixing zone is formed. The surrounding fluid is entrained and enhances the energy dissipation process. The flow velocity decreases significantly after leaving the pipe. This phenomenon explains why the outlet also contributes to energy loss. Losses in pipe turns. Any change in flow direction always produces additional energy losses. Elbows with smooth curvature produce smaller losses compared to sharp turns. Sharp turns increase turbulence and cause flow separation. Therefore, turn design strongly affects the efficiency of piping systems. Using large radius elbows is a good design practice.
Check your understanding number 11. Sharp angles in piping systems increase turbulence and energy losses, resulting in higher loss coefficients. Head loss in valves. Valves in piping systems cause energy losses because the flow experiences direction changes and area contraction. A partially closed globe valve produces strong flow separation and mixing, resulting in large head loss. A fully open ball valve provides a straighter flow path, and therefore much smaller energy loss. The constriction inside a globe valve increases local velocity and enhances energy dissipation. These differences are important when selecting valves for efficient system design. Industrial piping networks. Industrial piping networks connect various equipment to transport fluids within process facilities. These systems support functions such as fluid distribution, separation, and process integration. The complex layout makes flow analysis and energy loss evaluation very important. Good design minimizes head loss and improves operational reliability. System efficiency strongly depends on pipe diameters, fittings, and network layout. Pipes in series. For pipes in series, the flow rate through every pipe segment is the same. The total head loss of the system is obtained by summing the head losses of each segment. Any change in length, diameter, or roughness affects the total energy loss. This analysis is important to accurately estimate pump requirements. This concept is commonly used in long piping systems with multiple different sections. Pipes in parallel. In parallel pipe systems, each branch experiences the same head loss between inlet and outlet. The total flow rate is the sum of the flow rates in each branch. The flow splits according to the hydraulic resistance of each branch. The branch with smaller resistance carries a larger portion of the flow. This configuration is often used to control flow capacity and operational flexibility. Pump head requirements. Pump head is determined by the elevation difference between two reservoirs plus all head losses in the system. The energy supplied by the pump is used to lift the fluid and overcome frictional losses. The larger the elevation difference and friction losses, the greater the required pump head. This concept is fundamental in pumping system design. Accurate calculation prevents selecting an undersized or oversized pump. Check your understanding number 12. What determines the pump head in a system with reservoirs? B. The elevation difference between reservoirs and the head loss. Explanation. A. Incorrect, because flow velocity affects dynamic head but does not directly determine the total pump head. C. Incorrect, because the type of pump affects efficiency but not the fundamental calculation of pump head. D. Incorrect, because pipe diameter influences friction losses but is not the primary factor in calculating pump head.
Pump motor efficiency. The total efficiency of a pump system is the product of the motor efficiency and the pump efficiency. The motor determines how much electrical energy is converted into mechanical energy. The pump determines how effectively this mechanical energy is transferred to the fluid. Losses in either component directly reduce the overall system efficiency. Therefore, the motor and pump must be selected as an integrated unit.
Centrifugal pump curves. The pump operating point is determined by the intersection of the pump curve and the system curve. The system curve represents the relationship between flow rate and required head. The efficiency curve shows that the pump has a most efficient operating region. Operating far from this point increases energy consumption and wear. Therefore, proper matching between pump and system is very important.
Water flow disruption. In household piping systems, simultaneous water usage can cause pressure disturbances. When a toilet is flushed, the pressure in the shared pipe can suddenly drop. This change in flow rate can cause the shower temperature to become unstable. This phenomenon shows the importance of pressure balance in water distribution systems. Good system design can reduce user discomfort. Measuring water flow. Water flow rate can be measured using a simple method with a bucket and a stopwatch. The collected volume divided by the filling time gives the flow rate. This method is easy to perform and sufficiently accurate for rough measurements. This technique is useful for system performance checks or troubleshooting. This principle also introduces the basic concept of experimental flow rate measurement. Check your understanding number 13. To calculate water flow rate using a simple method, direct water into a bucket and measure the time taken to fill it.
Pitot and pitot-static probes. A pitot probe measures stagnation pressure, which is the pressure when the flow velocity is reduced to zero at the probe tip. The stagnation pressure represents the combination of pressure energy and kinetic energy of the flow. A pitot-static probe measures both stagnation and static pressures simultaneously. The difference between these pressures is used to calculate the flow velocity. This instrument is widely used in aerodynamics and fluid flow measurements.
Pitot-static probe use. Flow velocity is measured by connecting the probe to a manometer or a pressure transducer. Flexible tubing allows installation without significantly disturbing the main flow field. This method is commonly used in wind tunnels to obtain accurate velocity data. The measured pressure difference is directly converted into flow velocity. This principle is based on the Bernoulli equation.
Pitot-static probe details. The stagnation port is located at the probe tip and measures the total pressure of the flow. The static ports are small holes around the probe that capture the static pressure. This design ensures precise differential pressure measurement. Measurement accuracy strongly depends on the position and cleanliness of the pressure ports. Therefore, the probe must be properly installed and maintained. Flow through pipe constriction. A pipe cross-sectional constriction causes the flow velocity to increase and the pressure to decrease. This phenomenon is a direct consequence of the continuity and Bernoulli equations. The pressure and velocity conditions before and after the constriction must be analyzed. This change is usually accompanied by additional energy losses. This concept forms the basis of many obstruction-based flow meters.
Check your understanding number 14. What happens to fluid velocity and pressure when the flow passes through a constricted area in a pipe? C. Velocity increases and pressure decreases. Explanation. A is incorrect because a constricted area causes velocity to increase, not decrease, and pressure to drop, not increase, due to the Bernoulli principle. B is incorrect because velocity changes when the cross-sectional area changes and pressure decreases in constricted regions. D is incorrect because velocity increases, not decreases, in a constricted area, and pressure does not remain constant.
Obstruction flow meters. An orifice meter is simple and inexpensive, but causes a large pressure drop. A flow nozzle provides moderate accuracy with less pressure loss than an orifice. A Venturi meter offers high accuracy with relatively small pressure loss. The choice of device depends on the required accuracy and acceptable energy loss. All these devices operate based on flow acceleration in a constricted region. Orifice meter. Fluid passing through an orifice experiences an increase in velocity and a decrease in pressure. The pressure difference before and after the orifice is measured using a pressure transducer. This pressure signal is then converted into an electronic signal. The flow rate value is displayed digitally for monitoring. The operating principle is still based on the relationship between pressure and flow velocity. Orifice meter. An orifice meter measures flow rate by utilizing the pressure difference caused by a constriction. When the flow accelerates through the orifice, the pressure drops significantly. Components such as bellows and magnets are used to transmit the measurement signal. This system allows real-time flow rate readings. This device is widely used in industrial systems because it is simple and reliable.
Pressure variations in orifice meters. The pressure drops sharply as the fluid passes through the orifice. After the orifice, the pressure partially recovers, but does not return to its original value. The unrecovered pressure difference represents permanent energy loss. This loss is caused by turbulence and flow separation. The diagram clearly illustrates the concept of irreversible energy loss in flow. Positive displacement flow meter. This flow meter measures flow by displacing fixed volumes of fluid using impellers. Each rotation of the impeller represents a certain volume passing through. The double helical 3-lobe impeller design improves smoothness and measurement accuracy. This device is well suited for precise measurements in controlled systems. Its principle is more volumetric rather than pressure-based. Check your understanding number 15. Fluid flow measurement using impellers involves displacing fixed volumes with double helical 3-lobe impellers for efficient operation. Nutating disc flow meter. This flow meter uses a wobbling disc to measure the volume of fluid passing through. Each disc motion directly corresponds to a certain volume. The mechanical motion is then converted into a flow rate signal. This device is widely used for domestic and industrial water metering. Its advantages are simplicity, robustness, and reasonable accuracy.
Turbine flow meters. A turbine flow meter measures liquid flow rate by using the rotation of turbine blades inside the pipe. The rotational speed of the turbine is proportional to the flow velocity of the fluid. For gas or airflow, the same principle is used in portable wind speed measuring devices. The internal turbine design allows reasonably accurate measurements for many applications. This device is widely used for field measurements and industrial systems.
Paddle wheel flow meter. A paddle wheel flow meter measures flow rate by monitoring the rotation of a small paddle wheel in the flow. Each rotation represents a certain volume of fluid passing through. A sensor detects this rotation and converts it into an electrical signal. This device is relatively inexpensive and easy to install in pipelines. It is suitable for applications that do not require very high accuracy.
Check your understanding number 16. What key component is essential for a paddle wheel flow detection system? B. Paddle wheel sensor, housing, and lock nut for secure placement. Explanation. A. Incorrect, because the paddle wheel flow detection system uses a paddle wheel, not a double helical 3-lobe impeller. C. Incorrect, because a differential pressure transducer is used in other flow measurement systems, not paddle wheel systems. D. Incorrect, because a turbulence generator is unrelated to flow measurement and is not part of a paddle wheel system. Variable area flow meters. This flow meter operates based on the balance between the fluid flow force and the weight or spring force. The position of the float in a tapered tube indicates the flow rate. The larger the flow, the higher the float position. The scale on the tube directly shows the flow rate visually. This device is simple and often used for direct flow monitoring.
Ultrasonic flow meter. An ultrasonic flow meter measures flow rate by comparing the travel time of sound waves along and against the flow direction. The difference in travel time is directly related to the fluid velocity. This method does not require moving parts inside the pipe. Because it is non-intrusive, it does not disturb the flow. This technique is well suited for pipes that are difficult to modify.
Doppler effect flow meter. This flow meter uses the Doppler effect to measure the frequency shift of ultrasonic waves reflected by particles in the fluid. The frequency shift is proportional to the flow velocity. This device is very effective for fluids containing solid particles or bubbles. The transducer is usually mounted outside the pipe, making installation easy. This method is suitable for industrial applications with dirty or multi-phase flows.
Ultrasonic clamp-on flow meters. This flow meter is installed by clamping it onto the outside of the pipe without cutting or opening the system. Ultrasonic waves are used to measure the flow velocity through the pipe wall. This method allows measurements without stopping system operation. Because it does not directly contact the fluid, leakage risk is avoided. This device is very practical for field measurements and energy audits.
Check your understanding number 17. Non-intrusive flow measurement uses ultrasonic waves to determine flow properties without contacting the fluid.
Electromagnetic flow meters. An electromagnetic flow meter operates based on Faraday's law of electromagnetic induction. A conductive fluid generates an electrical voltage when it flows through a magnetic field. This voltage is proportional to the flow velocity. Because it has no moving parts, the device is very reliable and requires little maintenance. Its limitation is that it can only be used for conductive fluids. Vortex flow meter operation. A bluff body in the flow causes periodic vortex shedding behind it. The frequency of vortex formation is proportional to the flow velocity. A sensor detects this frequency and converts it into a flow rate signal. This method can be used for liquids, gases, and steam. Its design is relatively simple and robust for harsh process conditions. Hot wire probe functionality. A hot wire probe uses a thin, electrically heated wire to measure flow velocity. The cooling rate of the wire by the fluid depends on the surrounding flow velocity. The temperature change of the wire is translated into an electrical signal change. This method is very sensitive and suitable for turbulent studies.
However, the device is relatively fragile and requires careful handling.
Thermal anemometer system. A thermal anemometer system measures flow velocity using a sensor heated by an electric current. The system includes bridge circuits, filters, and amplifiers to process the signal. The processed signal is then sent to a computer for analysis. Its operating principle is based on convective heat transfer from the sensor to the fluid. This instrument is widely used in flow research and aerodynamics.
Check your understanding number 18. Which component is essential in a flow measurement system that uses a heated sensor? B. Bridge circuit, filters, and amplifiers for signal processing. Explanation. A is incorrect because ultrasonic wave generators are used in non-intrusive ultrasonic flow measurement, not systems with heated sensors. C is incorrect because paddle wheel mechanisms are mechanical components, unrelated to electrically heated sensors. D is incorrect because thermocouples measure temperature, not velocity, in heated sensor flow measurement systems.
Thermal anemometer probes. A single sensor probe can only measure the velocity component in one direction. A double sensor probe can measure two velocity components simultaneously. A triple sensor probe is used to analyze complex three-dimensional flows. The choice of probe type depends on the level of flow information required. The more sensors used, the more complete, but also more complex, the measurement system becomes.
Dual beam LDV system. This system uses a beam splitter to divide one laser beam into two. The two laser beams intersect and form a small measurement volume. Particles in the flow scatter light when they pass through this region. The scattered signal is captured by a photodetector for analysis. From this analysis, particle and flow velocities can be determined with high precision.
Fringe formation in LDV. When two laser beams intersect, an interference pattern of bright and dark lines called fringes is formed. The spacing between fringes determines the sensitivity and accuracy of the measurement. Particles moving through the fringes generate a periodic signal. The frequency of the signal is directly related to the particle velocity. Thus, the flow velocity can be calculated optically without contact. Turbulent pipe flow velocity profile. In turbulent flow, the velocity distribution in a pipe becomes flatter compared to laminar flow. However, near the pipe wall, the velocity still drops sharply due to viscous effects. The maximum velocity still occurs near the pipe's center line. This profile shape affects friction loss and heat transfer calculations. Understanding this profile is important in engineering flow analysis. Check your understanding number 19. In turbulent flow, the velocity profile is flatter compared to laminar flow, with a rapid decrease near the pipe walls due to viscous effects. Perfect. PIV system for flame study. A PIV system uses small seeded particles in the flow to visualize fluid motion. A pulsed laser forms a thin light sheet that illuminates the particles. A camera records the particle positions at two very close time instants. The particle displacement is used to calculate the flow velocity vectors. This technique is very useful for studying flow structures and flames.
3D PIV system for flow analysis. By using two cameras, this system can reconstruct a three-dimensional velocity field. A laser sheet illuminates the flow volume to be analyzed. Particle motion is recorded from two different viewing angles. The data are then processed to obtain 3D velocity vectors. This method allows much more detailed flow analysis. PIV analysis of hovering hummingbird. PIV techniques are used to map the airflow velocity field around hummingbird wings.
Colors are used to indicate the magnitude of the flow velocity. The pattern reveals complex vortex structures during hovering flight. This visualization helps to understand the lift generation mechanism in hovering. Such studies demonstrate the power of PIV in fluid biomechanics. 3D PIV system for air jet flow. A laser sheet is directed into the jet flow to highlight the flow structures. Stereoscopic cameras are used to capture data from two viewing angles. This method allows analysis of jet mixing with the surrounding flow. The velocity and flow direction patterns can be mapped in 3 dimensions. This information is very important for combustion and mixing studies.
Check your understanding number 20. What is the primary purpose of using stereoscopic cameras in jet flow visualization? B. To analyze jet mixing and velocity patterns in cross-duct flow fields. Explanation. A is incorrect because stereoscopic cameras do not affect the brightness of the laser sheet. Their role is to capture and analyze the flow behavior. C is incorrect because temperature variations are not the focus of stereoscopic cameras in this application. D is incorrect because adjusting laser intensity is unrelated to the function of stereoscopic cameras in flow visualization.
References. This list shows the main sources of figures and materials used in this chapter. The primary reference comes from the book by Chengel and Chimbala on fluid mechanics. Using these references ensures consistency with international standard literature. The visual materials and concepts are adapted for educational purposes. This emphasizes the importance of credible references in engineering education.